Let's delve into the mechanics of a firearm, stripping away the complexity to reveal the core principles at play. Imagine a simple firearm, a marvel of contained energy, a self-contained explosion waiting to happen. We're talking about a carefully engineered system, where every component plays a crucial role in delivering a projectile with incredible force. It's designed for a single explosive purpose: the controlled release of energy to propel a bullet towards its target. When you pull the trigger, you're not just releasing a hammer, you're initiating a rapid chemical reaction, a chain of events that unfolds in milliseconds. The firing pin strikes the primer, a small, sensitive component at the base of the cartridge. This impact creates a spark that ignites the gunpowder inside the cartridge, setting off a miniature inferno. Modern gunpowder is a carefully calibrated mix of nitrocellulose, a highly flammable compound derived from cellulose, and nitroglycerin, a powerful explosive that adds to the propellant's energy density. This mixture burns rapidly, almost instantaneously, to produce a surge of hot gas. This gas expands violently, building immense pressure inside the cartridge, far exceeding atmospheric pressure. The pressure pushes the bullet forward, forcing it down the barrel with tremendous acceleration. The barrel channels this force, acting as a guide and accelerator, ensuring the bullet travels in a single, predictable direction. Rifling, the spiral grooves inside the barrel imparts a spin to the bullet, stabilizing it in flight. The bullet exits the muzzle with a bang and a flash, a dramatic display of the energy unleashed. The sound is a complex phenomenon, a combination of the bullet breaking the sound barrier, creating a sonic boom, and the sudden release of high-pressure gas into the surrounding atmosphere, generating a powerful shockwave. On Earth, the bullet's journey is immediately challenged by gravity, the relentless force pulling everything towards the center of the planet, and air resistance, the drag force that opposes the bullet's motion as it pushes through the atmosphere. Gravity pulls it downward, constantly altering its trajectory from a straight line, while air slows it with every inch, gradually reducing its velocity and kinetic energy. The bullet's path is short and finite, a graceful arc dictated by the laws of physics, ultimately ending in the ground or, hopefully, a target. Every shot is a battle against these forces, a delicate balance between initial velocity, gravity, and air resistance. The story of a bullet on Earth is one of speed, a fleeting moment of supersonic travel, resistance, the constant struggle against the atmosphere, and inevitable decline, a return to Earth under the influence of gravity. But what happens when we take this process out of Earth's atmosphere, into the vacuum of space where gravity is weaker and air resistance is non-existent? That's a question that leads to some fascinating possibilities. Now let's leave Earth behind, that familiar blue marble we call home. We're about to embark on a journey to a place where the rules are fundamentally different, where the very fabric of reality seems to shift, and enter the vacuum of space. A realm of infinite possibilities, but also one of profound challenges. It's a place of stark beauty and unforgiving conditions. Here there's virtually no air, no atmosphere to breathe, no medium for sound to travel, just the vast emptiness between celestial bodies. No friction, meaning once something starts moving, it will continue moving in a straight line until acted upon by another force. No sound, a silence so complete it's almost deafening. Explosions happen without a whisper, and the roar of a rocket engine is only felt as a vibration. No resistance. Objects drift endlessly, unbound by the forces we take for granted on Earth. Gravity feels absent, though it's still very much present, just manifesting in a different way. But in orbit, you're actually in constant freefall, perpetually falling around the Earth or any other celestial body, creating weightlessness, a sensation of floating, of being untethered from the familiar pull of the ground. Everything, astronaut, gun, bullet, every object, regardless of its mass, falls together at the same rate in this continuous state of freefall, missing the planet thanks to immense sideways velocity. This delicate balance between gravity and velocity keeps objects in orbit. Up and down lose meaning, there's no inherent orientation in the void. It's a realm of perpetual motion. An object set in motion will continue moving indefinitely unless acted upon. Space is also a place of extreme temperatures, swinging wildly between scorching heat and absolute zero. With no atmosphere to buffer heat or cold, objects exposed to direct sunlight can become incredibly hot, while those in shadow freeze. The sun's radiation is raw and unfiltered, a constant bombardment of energy that can be harmful to living organisms and damaging to equipment. In this environment, our familiar rules don't apply. The physics we know and understand on Earth behave in unexpected ways. There's no air to slow a bullet, meaning it will travel much farther and faster than it would on Earth. No ground to pull it down. Its trajectory will be a straight line, not the familiar arc we see on Earth. The absence of friction and strong gravity changes everything from the way objects move to the way forces interact. Firing a gun here means rethinking what we know about ballistics and the behavior of projectiles. There's no bang, only the silent recoil of the weapon. No arc, just a straight line extending into the infinite expanse. No quick end to the bullet's journey. It will continue traveling until it encounters something to stop it. The laws of physics remain, the fundamental principles that govern the universe. But their effects are transformed, shaped by the unique conditions of the space environment. In space, every action plays out on a new cosmic stage, where the familiar rules of Earth no longer hold sway. Let's see what happens when we pull the trigger and explore the consequences of this simple act in this alien environment, a place where the ordinary becomes extraordinary and the impossible becomes reality. Does a gun even work in space without oxygen? On Earth, fire needs fuel heat and an oxidizer, usually oxygen from the air. But modern gunpowder is self-contained, it brings its own oxidizer. The primer ignites the gunpowder, which burns fiercely, even in a vacuum. The chemical reaction is internal, needing nothing from the outside, so in space the gun fires just as it does on Earth. The bullet is propelled by expanding gas exiting the barrel at full speed. There's no sound. Sound needs air, but the visual is spectacular, a flash of gas and glowing particles. An astronaut would hear nothing, only feeling the mechanical click through their suit. The gun's efficiency might even improve with no air to interfere. In the silent darkness, a gunshot becomes a brief, brilliant burst of energy. The mechanics are the same, but the experience is utterly alien. Newton's third law. Every action has an equal and opposite reaction. It's a fundamental principle that governs the interactions of objects in the universe. This law isn't just a theoretical concept, it's a practical reality that affects everything from the smallest particles to the largest celestial bodies. This law rules here too, even in the seemingly weightless environment of space. The absence of gravity doesn't negate the laws of physics. It simply changes the way those laws manifest themselves. In fact, the effects of Newton's third law can be even more pronounced in space due to the lack of other forces like friction or air resistance. On Earth, when you fire a gun, the recoil is absorbed by your body and the ground beneath you. The Earth's immense mass provides a stable platform, effectively neutralizing the backward force. You might feel a jolt, but the Earth barely notices. But in space, there's no ground, no friction to rely on. There's nothing to counteract the force of the bullet being expelled from the gun. This seemingly simple difference has profound consequences. Imagine you're an astronaut, floating freely. You fire a gun. The bullet shoots forward with considerable speed and energy, but you and the gun are pushed backward with an equal and opposite force. This is the direct result of Newton's third law in action. The system's total momentum, which was zero before the gun was fired, stays zero after. Momentum is conserved. The bullet's small mass, combined with its high speed, creates a certain amount of momentum in one direction. To balance that momentum and keep the total at zero, you'll move slowly in the opposite direction. If you weigh 1,000 times more than the bullet, meaning your mass is 1,000 times greater, you'll move at 1/1000th its speed, a much slower pace. It's not a dramatic blast that sends you hurtling through space. Instead, it's a gentle, almost imperceptible but unstoppable drift. Now consider what happens if the gun isn't fired from your exact center of mass. In that case, you'll start to spin, tumbling slowly through the void. Without a tether to hold you in place or thrusters to regain control, you can't stop the motion. You become a drifting, spinning satellite, a tiny object in orbit around your own center of mass. You are now at the mercy of Newton's laws, a testament to their unwavering influence. In space, every shot changes your position, altering your trajectory in subtle but definite ways. It's not just the bullet's trajectory that's affected. Your own path through space is altered as well. The consequences are inescapable, a testament to the elegant and interconnected nature of physics. Firing a gun here is as much about moving yourself and understanding the physics that govern that movement as it is about moving the bullet. In space, a bullet's journey is nearly endless. On Earth, air resistance and gravity quickly bring it down. In a vacuum, there's no drag, so the bullet keeps its speed, potentially forever. Newton's first law, an object in motion stays in motion unless acted on by another force. If fired in deep space, the bullet travels in a straight line for eons. But in orbit, gravity still matters. A bullet fired from the International Space Station could enter its own orbit around Earth. Fire in the right direction, and the bullet might circle the planet, returning to its starting point. You could, in theory, shoot yourself in the back after 90 minutes. The bullet becomes a tiny, deadly satellite, a reminder of orbital mechanics' strange power. In space, actions can come full circle, literally. Firing weapons in space isn't just theory, it's been tested. During the Cold War, the Soviets armed their Almaz space station with a 23mm cannon. In 1975, they test-fired it remotely using thrusters to counteract recoil. The test proved space-based weapons could work. American astronauts have carried survival pistols but not fired them in space. The TP-82 pistol was for emergencies after landing, not for use in orbit. We've brought guns to space and even fired one from a station. The challenges of recoil and function in a vacuum are real and solvable. Firing guns in space raises legal and ethical questions. The Outer Space Treaty of 1967 bans nuclear and mass destruction weapons in orbit, but is vague on conventional arms. This legal gray area allows for some weapon development, like anti-satellite missiles. There's a strong taboo against weaponizing space. Scientists see it as a shared fragile resource. Space conflict could create dangerous debris, triggering the Kessler syndrome and trapping us on Earth. The moral question, should we bring violence into the cosmos? Space exploration is about unity and wonder, not war. Turning orbit into a battlefield would betray that vision. Why ask what happens if you fire a gun in space? Because curiosity drives discovery. These questions help us apply physics to new frontiers, deepening our understanding. They inspire innovation. Recoil in zero gravity matters for every astronaut's movement. As we expand into space, these issues become practical, not just theoretical. Debating them now shapes a peaceful future beyond Earth. Ultimately, it's about our relationship with the universe, connecting simple mechanics to cosmic laws. Wonder and curiosity propel us to explore, understand, and reach for the stars.